Hello, my name is Trent Bocky, and I'm a part of an engineering firm hired to build a brand new shed on a site in Mooresland, Queensland. The location is currently an unused, vacant 0.41 hectare block of land ready to be built upon. To the west of the site is dense bushland, while in the other directions contain scattered residential homes. The intention behind building the shed is to allow the client to store a high range of automobiles. Before beginning the construction of the shed on the specified site, a detailed structural engineering design of the shed is required to be performed. The shed will be made of steel portal frames with aluminium wall cladding and custom wall roofing. The front side of the shed will have a large roller door which will be the only source of access. The scope of work compromises of the structural steel design to determine the shed's strength, which includes rafters and their connections, portal frame columns, purlins, girts, and roof and wall cladding. Struts, cleats, bracing, and base plates are examples of structural elements along with reinforced concrete that are outside the scope of work for the construction of the shed. A combination of Building Code of Australia and applicable Australian standards for structural design of buildings will be used to design the shed. I will now hand over to Bryce to talk about loads and wind factors.
As Trent said, my job was to analyse the wind, live and dead loads used that would affect the shed. A regional wind speed using the Australian standards was found to be 57 metres per second at a 500-year occurrence interval. As no people would be living or working in the shed, an importance level of 2 was also chosen. Normally, in this case, an importance level of 1 would be used. However, as you have a lot of high-priced valuables inside the shed, we thought that this would be the most appropriate option. Along with an importance level of 2, a terrain category of 2 was used. The relatively open terrain of Mooresland, compiled with the Australian standards, furthermore allowed for our wind loads to be calculated. To avoid any complications in design, a roof pitch of less than 10 degrees was also used. This allowed for less force to be affecting upper ridge height of the shed, and furthermore would allow for our wind loads to be calculated.
Hi, my name is Sam, and I was assigned the task of assessing whether the 200 UV 29.8 rafters and the 200 UC 46.2 columns would pass or fail under the critical loading conditions. Using the portal frame builder function in a structural design and analysis program SpaceGas, we generated a 3D model of the shed to be designed. The according wind, live, and dead loads were inputted accordingly. It was established that the critical loading conditions had the greatest effect on the middle frame of the shed. The bending moment diagram and shear force diagram for this frame were determined. From these values, and in accordance with the AS4100 standards, the imposed critical moments and forces were then calculated. It was established that the selected 200 UV 29.8 rafters and 200 UC 46.2 columns had adequate strength to sustain the critical loading conditions.
Hello, I'm Rowan, and I have been tasked with the completion of the joints and connections for our shed. Our shed utilises some M16 bolts, which have a 16mm diameter, along with a penetration buttwork. These have been calculated to fully accompany the load that the shed makes. These comply with the AS4100 standards, allowing our shed to be fully compatible in Queensland's environment. Thank you for listening to our design presentation. It's been my pleasure.